All right, so now we're going to talk about limits and how they relate to sequences. So this first one here, our definition, given a sequence an, if the terms an become arbitrarily close to a finite number L, as n becomes sufficiently large, we say that an is a convergence sequence and L is the limit of the sequence. So this works very much like the limits of different functions that we had back in Calculus 1. And again, this isn't that the sum of all these values is going anywhere. We're just looking at the actual terms in there. So if your different values in the sequence start getting closer and closer and closer to, say, the number 6, and eventually they either get very, very close to it but can actually reach it, or actually they all start becoming 6, we say that the limit as limit of an as n approaches infinity is equal to L. And if it's not convergent, we say it's divergent. All of this was basically the same thing that we had with functions, and in fact the theorem below. So limit of a sequence defined by a function. So consider a sequence an such that an equals some function as you start plugging in n. Okay, so the different values, consider them your x values, whatever your n value is. And again, this is for all n greater than or equal to 1. And if you want to make this 2 because you've got some issue with 1, that can be adjusted for as well. You can just change the numbering on things. At any rate, so if there exists a real number L such that this limit as x goes to infinity of the function is L, then we get the convergence of that limit equaling L. So again, it really works just how you would think with the general limits are concerned. What's happening with these different values as you put them in. And I've got the algebraic limit laws below. They are in your book, in the Calculus 2 book. However, these are the same limit laws you would have if all of these ANs and BNs were replaced by f of x and g of x, that sort of thing with different functions. Okay, so we'll go over these briefly. The number 1, that c is a constant. So for any constant c, the limit of that constant c, you just get that same number again, any real number. Also, number 2 simply means that if you've got the limit of some sort of constant multiplied by your sequence, you can pull out that constant ahead of it. All right, and in our setup here, the limit of the ANs equal A. So the limit of C times the ANs is going to equal C times A, because we know from number 1, the limit of just the constant is going to be the constant again. The sum and difference ones, same thing. You can break them up into the sum of differences. And the sum of the limits is the limit of the sums, just as it was back in Calculus 1. So if you add or subtract the limits of an and bn together, you're going to get a plus or minus b, depending upon if you're adding or subtracting them. Similarly, the limit, number 4, the limit of the products is the product of the limits. So if you take the limit of an times bn, you can break them up into the limit of all of an multiplied by the limit of bn, which gets a times b. And finally, the limit of the quotient is the quotient of the limit, with the expressed rule that your denominator can't be 0. And that means each individual one can't be 0 either. Can't be dividing by 0. Way back in algebra, we learned that. All right, so we're going to use these limit laws to rewrite this. You did something similar to this in Calculus 1 way back when. So we're going to use these limit laws first. First of all, limit of the ANs is 1, and the limit of the BNs is -1. Again, that's as n goes to infinity. And they do give us this nice little thing here that we're not dealing with anything that's going to be less than 0. Okay. So number 23. Well, this equals, we should write equals there first. We can break this up using I'm going to do number 3 first. So using 3, we take limit as n approaches infinity of 3an minus the limit as n approaches infinity of 4bn. And again, I used number 3. Use 3 there. Okay. Now this equals, I can use number 1 to bring the constants out. That's 3 times the limit as n approaches infinity of an minus 4 times the other limit. That's bn. And again, here I used number 1 in 2 separate occasions. And I can then just substitute in for what those limits are. Essentially, we have this, and that means we have 3 times 1 minus 4 times negative 1, which is 3 plus 4, which is 7. All right, we can do that. So this, we have a quotient, so let's break it up into the quotients here. This is limit of an plus bn over limit of an minus bn. And I'm using number 5 here. And then that, we're going to use number 3 on both the numerator and the denominator. So that's limit, and that should be, don't want to lose that. An plus limit of the n going to infinity of bn all over the difference of them. And again, I used number 3 for both the numerator and the denominator. And finally, we can just substitute in for what we know as the limits now. So this equals, we're looking at 1 plus negative 1 over 1 minus negative 1, which is 0 over 2, which is 0. And that's how you apply the algebraic limit laws to the sequence.